Good evening, and a very warm welcome to the Sleepy Club. This is a gentle sanctuary, a place where we embrace quiet knowledge, while slowly drifting toward the soft embrace of sleep. Here, our thoughtful stories share the wonders of existence, guiding your mind into rest without effort or hurry, and without the noise of the world. Before we begin this journey, I would love to hear where in the world you are listening from tonight, and what time the clock shows in your corner of the earth, whether you are wrapped in heavy blankets as the night grows deeper, or watching the sky soften with the first light of early morning. You are cherished and very welcome here. Tonight's story takes us on a slow and curious journey through the invisible and whispering landscape of your own nervous system. We will explore the magnificent network that works in silent harmony, the intricate dance of electrical impulses, and the quiet wisdom of the nerves that keep you whole. As you listen to these words, allow your shoulders to relax, your jaw to soften, and your breath to deepen into its natural rhythm. There is nothing you need to remember tonight, and nothing you need to understand perfectly. Simply let the ideas pass by gently, like soft clouds drifting across a moonlit sky. If you find comfort in these slow and thoughtful journeys, you are always welcome to like this video and subscribe to the Sleepy Club. It helps this calm little space grow, guiding others to find a peaceful place to rest and heal as well. Now, settle comfortably into the heart of your bed, feeling the weight of the day lift as you take a slow, deep breath in, and then gently let it go. Allow your eyes to close, your body to become heavy, and the noise of the world to fade into the distance. Leave behind whatever no longer needs your attention, and drift toward a calm and restful night. Now we begin our journey into the quiet and fascinating story of your nervous system, and the miraculous sparks that shape the very essence of your life. Tonight, we will listen closely to the quiet conversation happening inside you every moment of your life, the intricate and rhythmic dance of your nervous system. It does not shout, it does not demand your attention, but without its silent presence, there would be no movement, no memory, no feeling, and no thought. And as always, a gentle reminder: this video is for educational and entertainment purposes only, and should not be taken as medical advice. Somewhere inside you right now, a signal is zipping along a delicate thread of nerve fiber, perhaps a quiet update about the temperature of your toes, or a whispered instruction to adjust your posture ever so slightly. The most remarkable part of this journey is that you are not even aware it is happening. For the nervous system is the ultimate behind-the-scenes operator. It is your body's command center, your messenger service, and your crisis response team, all rolled into one, managing the complex symphony of your existence without demanding a single moment of your conscious attention. Unlike your heart, which beats rhythmically and insistently, or your lungs, which rise and fall in a visible rhythm, the nervous system is mostly invisible. It does not flex, it does not rumble or sigh. It simply thinks and orchestrates in the profound and sacred beauty of silence. At its core, this grand system is divided into two great departments: the central nervous system and the peripheral nervous system. The central nervous system is your brain and your spinal cord, the main headquarters where all major decisions are made. Think of it as mission control, humming quietly in the dark, issuing orders, evaluating reports, and processing everything from ancient memories to the smallest muscle movements. The peripheral nervous system, meanwhile, is the vast communication network that branches out from the spinal cord and brain stem, reaching into every fingertip, every organ, and every toe. If the central nervous system is the chief executive, the peripheral system is the team of messengers, sensors, and field agents, keeping the operation running smoothly out in the wild. It delivers information in both directions, flowing from the outside world in, and from the brain back out to the body. These two systems work together at astonishing speed. For when you touch something hot, nerves in your skin send that urgent signal to your spinal cord in a fraction of a second. The command to yank your hand back is already on its route, before you even fully register what has happened, which is not magic, but fast and efficient biology. But the nervous system is not just about speed. It also handles slower and more subtle forms of communication. Some signals are not racing toward action, but are drifting through circuits that evaluate, weigh, and integrate. Think of the difference between reflexively jumping away from a spider and slowly realizing that a friend's voice sounds a little sad tonight. Both responses come from the same system, but one is a lightning bolt, while the other is a cloud gradually forming in your mental sky. And here is where it gets even more impressive. For unlike many other systems in the body, the nervous system does not have just one job. The circulatory system pumps blood, and the digestive system processes food. But the nervous system thinks, feels, remembers, regulates, predicts, interprets, moves, reacts, adapts, and dreams. It is the stage, the script, and the actor all at once, using a mix of electrical impulses and chemical messengers to travel through the depths of you. It is like a telegraph line that sometimes switches to smoke signals, then back again, a hybrid mode of communication that explains why you can have both immediate reactions and long-lasting emotional effects. A sharp noise might make you jump, but a few carefully chosen words can stay with you for years. Same system, but different tools for the soul. Another fascinating feature is how the nervous system balances voluntary and involuntary actions, like how you choose to lift your arm. But you do not choose to sweat when you are nervous. You can hold your breath, but you cannot stop your pupils from adjusting to light, for the nervous system lives in this gray area between control and surrender. Some parts obey your will, while others go on with or without your permission, which is honestly a kind of gentle mercy. It would be exhausting to consciously regulate your heart rate every time you climbed a flight of stairs. The central nervous system itself is sheltered with a kind of reverence, the brain tucked away inside a bony skull, wrapped in 3 layers of protective membrane. It is bathed in cerebrospinal fluid, a clear cushioning liquid that acts as both a shock absorber and a nutrient delivery system. The spinal cord is similarly guarded, running through the vertebrae like a precious cable in a steel conduit, for nature seems to know how critical these structures are and takes no chances with their safety. Meanwhile, the peripheral nerves stretch outward like vines from a hidden root system, weaving into muscles, skin, and organs with delicate precision. Some of them are incredibly long, like the sciatic nerve which runs from the lower spine all the way down to your foot. That is a single nerve, several feet long, quietly ferrying messages up and down your leg all day long, without a fuss. It is easy to forget just how much is happening in every moment as your body receives sensory data from the environment, light levels, air temperature, and the pressure of the mattress beneath you. Your nervous system is filtering that information, deciding what to prioritize and what to ignore. For if it did not, you would be overwhelmed by raw input. You would not be able to focus on these words or anything else in this world. It is also in charge of keeping tabs on your internal world, monitoring blood pressure, glucose levels, and oxygen saturation. These are not just measured, they are responded to. And when something shifts, the nervous system nudges other systems into action. Whether it is speeding up your heartbeat, signaling hunger, or coaxing you into a yawn, it is not just a communicator, but a master coordinator. One of its most subtle tricks is how it maintains homeostasis, that balanced and just right internal state that your body constantly aims for. It is like trying to balance a stack of pebbles on a trampoline during a breeze. And yet, your nervous system does it effortlessly all the time. The whole structure is a marvel of evolution, refined over millions of years rather than being cobbled together by chance. Even the simplest creatures possess a version of this system, for without it, there is no awareness, no interaction, and no ability to survive. It's hard to imagine a living thing being alive at all without a way to detect, respond, and adapt to the world. In this sense, the nervous system is the very essence of being, a quiet and invisibly busy force that remains incredibly modest despite its vast responsibilities. If it had a personality, it would be that loyal friend who always shows up early, gets everything done, and never asks for any credit. So the next time you feel your heart race or a memory bubble up, know that it is just your nervous system gently at work, running the show without making a sound. If you had to nominate one cell for the role of overthinking everything, it would certainly be the neuron. These are not the bold or brawny types like muscle cells, nor the regenerating skin cells that constantly renew themselves. Neurons are thinkers and listeners, meticulous communicators that maintain a distinct air of introverted mystery under the microscope. They are the powerhouses of thought and sensation, designed to transmit information through a social life built entirely around connection. A single neuron might form more than 10,000 synapses with its neighbors, acting like a quiet intellectual at the center of a sophisticated gossip network. Each neuron has a distinctive shape, consisting of a cell body called the soma, a single long projection called an axon, and in a forest of branching extensions known as dendrites. If you picture a tree turned on its side, the dendrites are the leafy branches receiving signals, while the soma is the sturdy trunk handling core operations. The axon is the long root stretching outward, delivering information far and wide across the landscape of your body. The dendrites are where a neuron listens, covered in tiny receptors that receive chemical messages like dopamine, serotonin, and glutamate. These molecules encourage the neuron to fire its own message or tell it to stay quiet, while the cell decides if the whispers are loud enough to warrant a reply. That reply is an electrical impulse called an action potential, which travels down the axon like a wave of tumbling dominoes or ions rushing across a membrane. In many neurons, the axon is wrapped in a special insulating layer called myelin, which acts like a high-speed train line compared to a dirt path. A well-myelinated axon can transmit signals over 100 times faster than an unmyelinated one, ensuring that the message glides in on schedule and on polished rails. At the very end of the axon, the terminals cluster close to the dendrites of other neurons, without ever quite touching. Between them lies the synapse, a small but crucial gap across which neurotransmitters leap like microscopic messengers, carrying gossip between close-knit neighbors. This process is exquisitely timed and regulated, allowing a single neuron to repeat its cycle thousands of times every second. Neurons come in many shapes and sizes, from the tiny cells in your brain to the motor neurons in your spinal cord that stretch all the way to your toe. These long cells are like a single entity, running the length of a greyhound, a testament to cellular endurance and the distance these introverts will go to keep you moving. Sensory neurons pick up light, sound, and pressure, while motor neurons carry instructions to your muscles, and interneurons act as the middlemen who analyze and decide what to do. You are born with about 80 to 100 billion neurons, a vast number that carries you through a lifetime of thoughts and dreams. Unlike other cells, they do not regularly divide or replenish themselves, making them as specialized and irreplaceable as the memories they hold. Yet these neurons are not without flexibility, for they can change the strength of their connections and forge new pathways when you learn or remember. This adaptability means your brain is not a static machine, but a living and evolving network of endless possibilities. In a way, neurons are like those rare people who say just the right thing at the right time without demanding any attention. They have been with you from the very beginning, forming patterns while you were still floating in the amniotic quiet of the womb. They practiced their craft before you were even born, and they continue to guide you with perfect timing and precision, even now as you drift towards sleep. They exploded into activity, forming connections at a rate of nearly 1 million per second in the earliest months of life. That early neural bloom laid the groundwork for walking, talking, imagining, and learning. Even now, your neurons are still adjusting, refining, and reshaping their networks in response to your experiences. Despite their complexity, neurons are remarkably energy efficient, using precise bursts of energy only when needed. Their resting state, which is the calm between firings, is carefully maintained by a balance of charged particles inside and outside the cell. The sodium-potassium pump works like a gatekeeper, maintaining the delicate voltage across the membrane until it is time for action. It is quiet maintenance, always working behind the scenes to keep the balance. Neurons are also chemically diverse, as they do not all use the same neurotransmitters, and some even use multiple ones depending on the context. Dopamine plays a role in reward and motivation, while gamma-aminobutyric acid tends to have a calming and inhibitory effect. Glutamate, on the other hand, is an excitatory superstar, which is crucial for memory and learning. The chemical language of neurons is nuanced, layered, and far more sophisticated than we once imagined. Despite all this sophistication, neurons are still vulnerable, as they can be damaged by trauma, deprived of oxygen during a stroke, or affected by diseases like Alzheimer's or Parkinson's. But even in these challenges, the nervous system often finds ways to adapt. Neighboring neurons might strengthen their connections, new paths might be forged, and researchers around the world are working every day to understand how to help these cells heal or regenerate. For all their brilliance, neurons remain curiously humble, and they do not produce headlines like heart transplants or bionic limbs. They quietly power everything that makes you who you are, including your thoughts, your voice, your hopes, and your sense of time. They are the invisible network that lets you imagine, remember, love, and decide what kind of pizza you want. So, the next time you pause mid-thought or feel an idea spark into life, it is worth appreciating that somewhere deep in your brain, a neuron, or maybe a small chorus of them, just fired in elegant harmony. There is no grand performance and no loud announcement, just a gentle electric whisper from one introverted cell to the next. If you have ever been jolted awake by a brilliant idea, or reflexively pulled your hand back from something hot, you have just experienced the silent spark of an action potential. There is no noise and no flash, just a whisper of electricity rushing down a microscopic cable. It is one of the most astonishing tricks of biology, a tiny zap inside a single cell that somehow helps you read, dance, remember birthdays, and occasionally forget why you walked into the kitchen. At the heart of this marvel is the humble neuron, and at the heart of the powers of the neuron is its ability to generate an electrical impulse. It does this not with batteries or wires, but with a delicate dance of ions, which are electrically charged particles like sodium and potassium that flow in and out of the cell at just the right moments. It is not unlike the ebb and flow of a tide, except that this tide moves in milliseconds and carries your every thought with it. To understand how neurons fire, we need to peek inside their membranes, which are the thin and flexible boundaries that separate the inside of the cell from the outside world. These membranes are not just barriers, they are incredibly selective gates equipped with tiny protein channels and pumps that carefully control what moves in and out. When a neuron is at rest and not actively firing, it is in a state called the resting potential. Imagine it as a calm beach before the first wave rolls in. During this state, the inside of the neuron is slightly more negative than the outside. This difference in charge is known as the membrane potential, and it is usually about 70 millivolts. This is not much in absolute terms, but in the cellular world, that is like holding a tightly wound spring, ready to uncoil at the slightest provocation. This charge difference is maintained by the sodium-potassium pump, a protein that tirelessly exchanges ions across the membrane. For every 3 sodium ions it pushes out, it brings in 2 potassium ions. This creates a high concentration of sodium outside the cell and a higher concentration of potassium inside. It is a bit like storing firewood just outside the door while keeping a few logs handy inside, ready for quick use, but not enough to start a bonfire. Then comes the stimulus, a small change in the environment, perhaps a message from another neuron, or a touch on the skin. If the stimulus is strong enough, it nudges the membrane potential closer to what is called the threshold. This threshold is usually around 55 millivolts, and if the neuron reaches this magic number, the gates fly open. When those gates open, everything changes in a flash. Voltage-gated sodium channels, which are specialized protein pores in the membrane, snap open and sodium ions rush into the cell. It is a flood, and the inside of the neuron, which was once negatively charged, quickly becomes more positive. This rapid change in electrical charge is the action potential, but it does not just sit there. It moves like a spark racing along a fuse, for the depolarization at one segment of the axon causes the sodium channels of the next segment to open, and then the next, and the next. It is a self-propagating wave, not unlike a stadium doing the wave, but with far more precise choreography and fewer distractions. As the action potential travels down the axon, the original segment begins to reset. Sodium channels close and potassium channels open, allowing potassium to flow out of the cell. This repolarizes the membrane, returning it to a more negative state. Eventually, everything settles back into the resting potential, which is a little like cleaning up after a party when the excitement is over, and it is time to get the chairs back in place and refill the snack bowls. There is also a brief period during which that part of the neuron cannot fire again, which is called the refractory period. It ensures that the action potential only moves in one direction and prevents the neuron from firing too rapidly. Think of it as a mandatory coffee break between tasks, where even neurons need a moment to catch their breath. Now, if the neuron happens to be wrapped in myelin, which is the insulating layer provided by glial cells, the signal jumps between gaps in the myelin called nodes of Ranvier. This is known as saltary conduction, and it dramatically speeds up signal transmission. Instead of crawling down the axon inch by inch, the signal leaps from node to node like a frog, hopping across lily pads. It is energy efficient and lightning fast. Interestingly, the action potential itself does not change in size, for it is all or nothing. If the threshold is reached, the neuron fires at full strength. If not, it does not fire at all. There is no in-between and no partial effort. It is a yes or no decision. This binary switch keeps everything clear and consistent. What varies is how frequently a neuron fires, not how strongly it pulses. A loud sound or a painful stimulus might cause a rapid burst of action potentials, while a gentle breeze might produce only the occasional pulse. This system of electrical signals allows for extraordinary precision, where a single neuron might fire only a few times per second, while others can manage hundreds of firings in that same span. These patterns, the rhythm and frequency of zaps, are what the brain uses to encode different types of information. It is not just about whether a neuron fires, but how often and when, like a Morse code built out of electricity and silence. And this entire process happens incredibly fast, as an action potential can be over in just a few milliseconds. In that time, it can travel several feet along an axon, which is fast enough to let you blink before a bug hits your face. or pull your hand away from a hot stove before your brain fully registers the pain. The phrase split-second decision is not just poetic, for your neurons are literally operating in fractions of seconds all the time. While this might sound mechanical, the implications are profoundly human. These tiny sparks, individual action potentials happening millions of times per minute, make up the foundation of thought, sensation, movement, memory, and emotion. Whether you are writing poetry, learning to juggle, or just deciding which socks to wear, it is all action potentials humming quietly along your neural highways. What is more, this electrochemical system is incredibly adaptable, as neurons can become more or less sensitive to stimulation over time. Depending on use, they can change how many receptors they have, adjust their firing threshold, or even remodel their connections entirely. Your thoughts are not just passengers riding on fixed train tracks, for they help lay the tracks as they go, subtly rewiring the brain through experience and repetition. On a molecular level, none of this is glamorous, as it is just ions moving across membranes, proteins flipping open and shut, and gradients balancing like chemical seesaws. But collectively, it gives rise to everything that makes us who we are. The big abstract ideas like imagination, memory, or fear all begin with something as humble as a sodium channel opening at the right moment. And while the term electrical signal might evoke something noisy or jarring, in the nervous system, these sparks are silent. There is no crackling sound or bright flash, and no visible arc. It is a quiet current, softer than a whisper, moving invisibly through tissue, guiding the world inside your head and body. Every time you take a breath, feel a tickle, recall a name, or reach for a cup of tea, you are witnessing the result of countless action potentials. Each one is a perfect example of nature's quiet engineering, a system that values speed, but also grace, efficiency, and reliability. So while your heart may beat and your lungs may sigh, the real choreography of your life is happening in the silence between sparks, where thought begins and action waits just a millisecond away. Imagine a world where no one ever spoke directly, where messages were passed across small gaps by carefully trained messengers carrying coded packages. Welcome to the synapse, the tiny but mighty gap between neurons where information is not shouted across, but elegantly relayed in chemical whispers. This microscopic space, typically less than 1/10,000th of a millimeter wide, is the meeting point between the end of one neuron and the beginning of another. But they do not actually touch, instead, like polite conversationalists, maintaining a respectful personal bubble. Neurons pass their messages across this gap using chemicals known as neurotransmitters. A neuron has just fired an action potential, that brief but powerful electrical impulse that races down its axon. At the very end of that axon, things branch out into tiny structures called axon terminals, which are loaded with special packages called synaptic vesicles. These are tiny bubbles filled with neurotransmitters, each one like a miniature message in a bottle. When the electrical signal arrives at the terminal, it does not jump the gap directly, for electricity does not make that kind of leap. Instead, it triggers a chemical chain reaction, as the action potential causes calcium channels to open, allowing calcium ions to flood into the terminal. This influx is the cue for those synaptic vesicles to move toward the membrane, fuse with it, and release their neurotransmitter contents into the synaptic cleft, which is the space between neurons. And just like that, the message has transformed from electrical to chemical. Now the neurotransmitters drift across the synaptic cleft, which may be incredibly narrow, but is filled with potential. On the receiving side, the dendrite of the next neuron, there are specialized proteins called receptors. Each receptor is designed to bind to a specific type of neurotransmitter, a bit like a lock that only fits one key. When the neurotransmitter finds its matching receptor, it binds to it and causes a change in the receiving neuron. This might trigger an action potential of its own, or it might inhibit one from forming, depending on the kind of neurotransmitter and the receptor it binds to. Some neurotransmitters are excitatory, encouraging the next neuron to fire. And glutamate is a classic example. It is the go-getter of the neurotransmitter world, playing a major role in learning and memory. Others are inhibitory, dampening the chance of firing. And GABA, or gamma-aminobutyric acid, is the brain's gentle hush. It helps to calm overactive circuits and prevent neural chaos, acting like the chemical equivalent of someone placing a hand on your shoulder and gently saying, "Maybe let us not panic just yet." Then there are the modulators, which are neurotransmitters that do not directly trigger or prevent firing, but influence how responsive neurons are to other signals. Dopamine, for instance, helps shape motivation, reward, and movement, while serotonin plays a role in mood, appetite, and sleep. Norepinephrine is involved in alertness and arousal, yet these chemicals do not yell instructions. They simply tweak the volume knob to adjust how loudly other signals are heard. It is important to note that the same neurotransmitter can have different effects depending on where it lands. Dopamine in one part of the brain might be about pleasure and anticipation, but in another, it is about motor control. Serotonin, depending on the receptor it binds to, might either excite or inhibit a neuron, for context is everything. Once the neurotransmitter has done its job, it does not just hang around, as the synapse is a place of quick exchanges and not lingering conversation. There are several ways the signal is cleared, sometimes as the neurotransmitter is broken down by enzymes, which are molecular scissors that cut it into inactive pieces. Other times it is taken back into the original neuron through a process called reuptake, which is like recycling the message for future use. Some drugs, like certain antidepressants, work by blocking this reuptake to allow serotonin to stick around a bit longer and have a more prolonged effect. The efficiency of this whole system is mind-boggling, for a single neuron can form thousands of synapses. Across the human brain, there are estimated to be over 100 trillion synapses, which is more connections than there are stars in the Milky Way. And yet, each one is exquisitely precise. Messages are delivered, interpreted, and erased in fractions of a second, creating the seamless experience of thought, sensation, and movement that we take entirely for granted. Not all synapses are the same either, for while chemical synapses are the most common and used neurotransmitters to send signals, there are also electrical synapses. These are direct connections between neurons, using gap junctions that allow ions to flow freely between cells, making them faster but less flexible. Chemical synapses, though slightly slower, offer more nuance and control, which is likely why evolution favored them for complex tasks like emotion, memory, and decision-making. The balance of neurotransmitters at synapses is delicate and constantly changing, and learning involves strengthening some synaptic connections while weakening others. This process, known as synaptic plasticity, is what allows your brain to adapt, grow, and recover from injury. It is also why practicing something, whether it is playing the piano or speaking French, literally reshapes your brain as the synapses involved become more efficient, more responsive, and more tightly connected. Sometimes this balance is disrupted, for too little dopamine can lead to Parkinson's disease, a condition marked by tremors and slowed movement. Too much dopamine activity in certain pathways is associated with schizophrenia, while a deficiency in serotonin has been linked to depression. Disruptions in GABA signaling can lead to anxiety or seizures, and in these cases, medications may be used to help restore balance by influencing neurotransmitter production, breakdown, or reuptake. This is also how many recreational drugs work, as substances like caffeine, alcohol, nicotine, and more potent agents like cocaine and MDMA all hijack the synaptic process in various ways. They may flood the synapse with dopamine, block reuptake of serotonin, or mimic natural neurotransmitters to produce euphoric or stimulating effects. It is a powerful system, and even tiny chemical tweaks can have enormous effects on mood, behavior, and perception. All of this happens without a sound, with no crackling static, no flashing light, and no fanfare. Just molecules drifting across microscopic spaces, locking onto their targets and triggering changes that ripple across networks of cells. It is chemical poetry written in an alphabet of amino acids and carried by invisible waves. If you zoomed out far enough, those trillions of synaptic conversations form the basis for your personality, your habits, your memories, and your quirks. That moment of laughter, the sudden memory of a childhood room, and the decision to have pancakes instead of toast are all rooted in neurotransmitters crossing tiny gaps and binding to waiting receptors. It is easy to think of the brain as a computer full of cold logic and blinking circuits, but synapses tell a different story. They are not mechanical, but organic, fluid, and dynamic, able to strengthen, weaken, grow, and vanish entirely. They are shaped by experience, stress, sleep, and sunlight, and they are influenced by what you eat, how you move, and how you feel. They are not just communication hubs, but the places where your life gets translated into biology, happening quietly, reliably, and continuously. You do not have to ask your synapses to work. They simply do, like the soft rustle of leaves in a forest, whispering constantly beneath your awareness to carry the messages that make you who you are. Have you ever touched something hot and yanked your hand back before you even had time to shout? Or sat on a doctor's table and watched your leg kick out involuntarily when they tapped just the right spot below your kneecap? These quick and automatic movements might feel like magic, but they are actually the work of one of the body's most elegant shortcuts, known as the reflex arc. Reflexes are the nervous system's way of handling things without bothering the brain, acting as if the spinal cord is quietly saying that it has this situation under control. It's a brilliant system for staying safe and responsive when time is of the essence. Because when it comes to survival, milliseconds matter. Let us break down what is happening when a reflex kicks in, such as when you touch a painfully hot stove burner, a cup of coffee gone rogue, or perhaps a freshly microwaved plate that you were certain had cooled down. The moment your skin detects that heat, sensory receptors in your fingers send an urgent signal through sensory neurons toward the spinal cord. Instead of waiting for that message to go all the way to the brain to be processed, the spinal cord takes charge and immediately sends a return signal via motor neurons to the muscles in your arm and hand, telling them to pull away. This shortcut from sensory input to motor output, bypassing the brain's involvement until after the fact, is what is called a reflex arc. It is not that your brain is lazy or unimportant, but in situations like this, speed is more valuable than a committee meeting. You will still feel the pain, of course, but only a fraction of a second after your body has already acted to protect itself. The reflex arc is composed of just a few essential parts, including the sensory receptor, the sensory neuron, the integration center in the spinal cord, the motor neuron, and the effector, which is usually a muscle or gland. It is a tightly coordinated relay team, with each part passing the baton with precision. Reflexes come in a variety of flavors, and some are monosynaptic, meaning the sensory neuron communicates directly with the motor neuron, with no middleman. These are the fastest reflexes, like the patellar reflex, which is the famous knee jerk. When a doctor taps that little spot just below your kneecap, it stretches the tendon and the muscle underneath, and stretch receptors in the muscle detect that change to send a signal to the spinal cord. The response is a quick command to contract the muscle and extend the leg, which is simple, clean, efficient, and strangely satisfying to watch. Other reflexes are polysynaptic, involving one or more interneurons between the sensory and motor neurons, making them slightly slower but offering more complexity and coordination. The withdrawal reflex, which makes you pull back from something painful, is a good example, as the muscles in the affected limb contract to move you away, while other muscles might relax or tighten to maintain balance. Your body does not just react, it reacts wisely. And there is even a delightful little companion to the withdrawal reflex called the cross-extensor reflex. If you step on something sharp with your bare foot, your injured leg pulls back, while your other leg automatically stiffens to support your weight and keep you from falling over. You did not consciously think to adjust your posture to compensate, for your spinal cord handled it before you had a chance to be clumsy. While most reflexes are there to protect you or maintain posture and balance, not all are strictly physical. Some reflexes are visceral, meaning they involve internal organs, such as the gag reflex, or the way your pupils automatically constrict in bright light. These are still reflexive actions, protective and automatic, regulated by circuits that prioritize survival and comfort. Your body knows that bright sunlight might damage your retinas, or that something lodged in your throat could be dangerous, and it acts accordingly without a single word from you. Reflexes also play a huge role in development, for babies come equipped with a variety of primitive reflexes that help them survive and interact with the world in their earliest days. The rooting reflex, for instance, causes a baby to turn its head toward a touch on the cheek, which is helpful when trying to find a source of food. The palmar grasp reflex makes their tiny fingers wrap around yours when you place a finger in their palm, a sweet and silent bond of strength. These early reflexes gradually fade as the nervous system matures and voluntary control takes over, but they remain an important sign of healthy neurological development. Testing reflexes is actually one of the simplest and most effective ways for doctors to assess the health of the nervous system. Reflexes that are too strong, too weak, or entirely absent can indicate a problem somewhere along the neural pathway, whether it is in the sensory input, the motor output, or the integration center itself. A sluggish reflex might suggest nerve damage, while an exaggerated one could point to issues in the brain's control over spinal reflexes. It is like checking the wiring in a circuit, for if the light does not flicker when you flip the switch, you know something is not quite right. Reflex arcs are also one of nature's oldest tricks, as you do not need a fancy brain to have a reflex. Even simple organisms like jellyfish or worms exhibit reflexive responses, and while they do not philosophize or play chess, they react to touch and light with perfect reliability. These basic circuits are evolutionary gold, being fast, reliable, and essential, likely predating the evolution of brains altogether. Interestingly, not all reflexes are rigid and unchanging, for with enough repetition and training, some reflexive responses can be reshaped or even suppressed. Think about athletes or musicians whose movements are so well practiced that they appear automatic. These are not reflexes in the strict neurological sense, but they demonstrate how the nervous system can build efficient and near instantaneous responses through repetition. Over time, what began as deliberate effort becomes almost reflexive, and there are also reflexes you can consciously override. If someone tosses you a ball, your instinct might be to duck, but with practice, you learn to reach out and catch it instead. Or perhaps you have suppressed a sneeze or held your breath underwater. Situations that show how the conscious brain and the reflexive spinal pathways can sometimes negotiate a truce, depending on the context. And yes, there are occasional quirks, as sometimes reflexes misfire or get exaggerated. Ever had a twitchy eyelid after too much caffeine? That is a hyper-excitable reflex arc at work. Or those odd little muscle jerks as you are falling asleep called hypnic jerks, which scientists believe are leftover reflexes from earlier stages of evolution. Your brain briefly thinks you are falling, and your body reacts with a sudden jolt, which is slightly embarrassing but entirely normal. At core, reflexes remind us that the body is more than just a vehicle directed by conscious thought. There is a whole world of intelligence embedded in your spinal cord, a network of rapid responders that keep you safe, stable, and upright without needing your explicit input. They are the security team that operates in the background, ready to act before you even know there is a problem. So whether you are dodging a wayward soccer ball, pulling your hand away from a cactus, or blinking at the sudden flash of a camera, your reflexes are quietly at work. They handle the fast stuff, so your brain can take its time deciding what to do next. A silent and swift team of neural shortcuts that keep you on your feet, often quite literally, without asking for credit. If you could somehow shrink yourself down to the size of a molecule and wander through the human brain, you would not find a neatly labeled control room with blinking lights or tidy wiring like in a computer. You would find something far more organic. A sprawling, branching, and ever-shifting landscape. It would feel less like a machine, and more like a dense and whispering forest. In this forest, neurons do not work alone, but form vast networks called neural circuits that carry out everything from simple reflexes to the complex ballet of thought. A single neuron can do incredible things, receiving input and making decisions. But it is when neurons link up in structured patterns that the real magic happens. Neural circuits are groups of interconnected neurons that process specific types of information, forming the living highways and backroads of your nervous system. The basic structure of most circuits can be broken down into three main roles, which are sensory input, integration, and motor output. It is a simple framework, yet it is the foundation for everything from scratching your nose to composing a symphony. Sensory input is where the journey begins, with specialized receptors picking up information from the world around you, or from within your own body. These receptors come in all flavors, such as mechanoreceptors for touch and pressure, photoreceptors for light, chemoreceptors for taste and smell, and thermoreceptors for temperature. They convert environmental signals like the chill of a breeze or the texture of a fuzzy blanket into electrical impulses that neurons can understand. These impulses travel along sensory neurons toward the central nervous system, and you can think of them as messengers carrying incoming news. These messages do not have meaning yet, for they are raw data, bits and pieces of sensation waiting to be assembled. That assembly happens in the integration centers, mainly in the brain and spinal cord, which act as the processing hub, takes multiple inputs, and decides what to do next. Integration is the nervous system's version of deliberation, where it receives multiple messages, filters out the noise, recognizes patterns, and compares current inputs with memories and expectations. This is why your nervous system does not overreact to every single piece of sensory input. You might not notice the feeling of your socks until someone mentions them, because your brain filters out that data as unimportant at the moment. But if the socks are suddenly soaked with cold water, your sensory neurons will send a more urgent message, and your brain will decide it is time to pay attention. The decision-making process is not just about receiving information, but about weighing its relevance and determining whether action is needed. Once a decision is made, motor output carries it out, as motor neurons transmit commands from the brain or spinal cord to muscles or glands. Whether it is moving your arm, adjusting your breathing, or producing saliva, it is the final step in the quiet dance of your internal world. Motor neurons are the final link in this silent circuit, translating your deepest intentions into graceful and meaningful action. Whether it is a voluntary wave hello to a friend, or the involuntary shrinking of your pupils in response to a sudden light, these neurons act as the bridge between your will and the world. Within this basic structure, neural circuits vary tremendously in their complexity, ranging from the simple reflex that jerks your hand away from a hot pan, to the millions of neurons firing in precise patterns to solve a math problem or recognize a familiar face. These complex circuits do not just sit in one part of the brain, but span across multiple regions, forming networks that handle everything from visual processing to the delicate regulation of your emotions. The visual cortex, for instance, does not just receive light data from the eyes. It analyzes shapes, motion, depth, and even color before sending that data to other regions that interpret it within the context of your life. Different neural circuits help you decide if a shape is a bird flying past your window or perhaps just a plastic bag dancing in the wind, bringing together sight, memory, and past experiences in a single quiet moment. One of the most remarkable things about these neural circuits is that they are not static, for they possess the ability to grow, shrink, reroute, and rewire. This is thanks to a property called neuroplasticity, the beautiful ability of a nervous system to adapt and change itself based on every experience you encounter. When you learn a new skill or form a precious memory, you are changing the structure and strength of your neural circuits. As new connections form and old ones fade away, practice literally shapes the way your brain is wired, much like playing a piano scale that feels clunky at first, but with repetition becomes second nature as the communication between neurons improves. Even when you are not actively learning, your neural circuits are in a constant state of maintenance, where some are reinforced by routine, while others atrophy from disuse. The brain, it turns out, is a bit like a garden, where connections used regularly grow strong, while others fade like untended paths in the deep woods. This metaphor of a forest is more than just poetic, for in many ways, the brain structure resembles a complex ecosystem where neurons stretch and branch like trees. Glial cells act like gardeners and caretakers, pruning synapses, providing nutrients, and clearing away the debris of the day. Some areas are densely packed like the thicket of a jungle, while others are more spacious, allowing information to meander, loop, and echo in layers of response. Because of this complexity, the brain is often compared to a computer, but this analogy has its limits, for computers are rigid and modular, while the brain is fluid and deeply interconnected. Neural circuits do not just store data, they interpret it and imbue it with meaning, adapting to changing conditions, and even self-correcting when things go awry. Understanding how these circuits work and sometimes fail is a vast area of research, as we have only just begun to map the connectome. The full map of neural connections in the brain is like trying to chart every tree and vine in an unimaginably vast jungle, where every discovery brings us closer to understanding what it truly feels like to be human. The world is a loud, bright, flavorful, and textured place, and yet all of that richness exists only as raw data until your nervous system gets involved. You do not actually see light or hear sound directly, for what you experience is your brain's interpretation of electrical signals sent by specialized receptors. Reality is not just what is out there, it is what your brain tells you is out there. And it is doing that constantly and seamlessly without your conscious awareness. Your skin is your largest sensory organ, and it is loaded with receptors for pressure, vibration, temperature, and pain. These receptors are surprisingly specialized, with some detecting the brush of a feather, while others are tuned for deep pressure or the buzz of a phone in your pocket. There are thermoreceptors that respond to heat and cold, and nociceptors that detect pain, which is an essential guardian that tells you when tissue is damaged or when to back away from danger. Once these receptors are activated, they send signals through sensory neurons to the spinal cord, and then up to the brain, where they are routed to the somatosensory cortex. This is a strip of brain tissue where different parts of your body are represented in a rather peculiar map, where your hands and lips take up a disproportionately large area because they are incredibly sensitive. Your back, meanwhile, is represented in a much smaller area, which is why you can scratch around for ages and still not find the exact itchy spot. Each of these signals is a thread in the tapestry of your physical existence, woven together in the quiet dark of your mind to create the feeling of being alive. Now, let us turn our attention to taste, a sense we so often associate with the simplest pleasures, like the warmth of your morning coffee or the crisp joy of a particularly crunchy pickle. Your tongue is adorned with tiny structures called papillae, and nestled deep within them are the taste buds, which are microscopic clusters of receptor cells. These delicate cells detect 5 primary tastes, including sweet and salty and sour and bitter, and that savory essence known as umami. Hatiumonsu, that savory essence known as umami. When you eat, the chemicals in your food dissolve gently in your saliva and interact with these receptors to send signals to your brain through the facial and glossopharyngeal nerves. The brain takes this humble information and weaves it together with your sense of smell and the texture from your touch, and even the visual beauty of the meal, to create the rich experience of flavor. This is why food seems so dull when you have a cold, because your olfactory input is muffled, and your brain is left to build its world with limited materials. The sense of smell is both ancient and direct, bypassing the usual relay stations of the brain to go straight to the olfactory cortex and the limbic system. This is the heart of emotion and memory, which is why a single whiff of sunscreen can send you drifting into a vivid memory of a childhood beach trip. It is not merely nostalgia, but the way your neural architecture is built, beginning with odor molecules floating through the air and into your nose. They dissolve in the soft mucus and bind to receptors on specialized neurons, where humans have around 400 different types of olfactory receptors. Each type responds to different molecular features, and the brain interprets the combination of activated receptors as a unique scent. From the smell of fresh cut grass to the comforting aroma of baking bread, hearing begins when air vibrations and pressure waves enter your ear, traveling down the auditory canal to reach the eardrum and cause it to vibrate. These vibrations are transferred through 3 tiny bones in the middle ear, known as the hammer, and the anvil, and the stirrup, which amplify the signal as it journeys into the cochlea. The cochlea is a snail-shaped structure filled with fluid and lined with sensory cells, where pressure waves create gentle ripples that bend tiny hair cells at specific points. High-pitched sounds move one end of the cochlea, while low-pitched sounds affect the other, and this movement opens ion channels to generate electrical signals. These signals travel along the auditory nerve to the auditory cortex, where raw data is transformed into a whisper, or a thunderclap, or the melody of your favorite song. Vision is arguably the most dominant of the senses, and it is entirely a story about light, as photons enter your eye through the cornea and the lens. They focus the light onto the retina at the back of the eye, where rods and cones convert that light into electrical signals. Rods are incredibly sensitive and handle the soft light of the night, while cones respond to the vibrant colors of red and green and blue. By comparing the input from these cones, your brain constructs the full spectrum of color as signals travel through the optic nerve to the visual cortex. Interestingly, what you see is not just a recording, for the brain fills in gaps and corrects distortions, and even patches over the blind spot where the nerve exits the retina. You never notice the hole in your visual field, because your brain is an artist, interpreting and adjusting your surroundings in real time. Then there is the sixth sense that often flies under the radar, known as proprioception, which is your internal awareness of where your limbs are in space. It is what allows you to touch your nose in the dark, or walk up a flight of stairs without ever watching your feet. It relies on stretch receptors in your muscles, and tendons, and joints, which send constant updates to the brain about the position of your body relative to itself. This information is integrated in the cerebellum and the somatosensory cortex to create a stable sense of posture and movement. Without this silent sense, even the simplest tasks would become difficult, and those who lose it must rely entirely on watching their own arms and legs to guide their every move, even for a simple cup of tea. All of these sensory systems, including touch and taste and smell and hearing and sight and proprioception, are fundamentally about converting the world into neural signals. The diversity of these receptors and the speed of processing make this one of the most impressive feats of your nervous system. What is truly astonishing is how unified and fluid your reality feels, for you do not experience these as separate streams, but as a single moment where the scent of rain and the feel of sunlight are blended into harmony. Your sensory systems are always scanning and always reporting back in a conversation that makes your life richer. They are the windows to your world, cleaned and maintained by your nervous system, with a quiet excellence that rarely receives thanks. Picture yourself deciding to reach for a morning cup of tea, an ordinary action that is actually a symphony of timing and balance. This motor magic begins with intention in the brain, starting in the motor cortex, within the frontal lobe of your cerebrum. It carefully plans your movements, deciding exactly how far your arm needs to stretch, how much force to use, and which muscles to activate, all before your hand even begins to lift. Once the motor cortex has a plan, it sends signals down through the brainstem and into the spinal cord, traveling along the upper motor neurons, which act as the long-distance messengers of the central nervous system. Think of them as the executive branch of movement, issuing high-level instructions to the lower motor neurons that connect directly to your muscles. These lower motor neurons live in the spinal cord and extend their axons out through the peripheral nervous system, and when they receive a command, they trigger a remarkable release of a chemical called acetylcholine at the neuromuscular junction. This tiny gap between a nerve ending and a muscle fiber is where the message changes its form. Acetylcholine acts like a green light at a traffic signal, binding to receptors and setting off a chain reaction where calcium floods in, proteins shift, and the muscle finally contracts. Whether your tea is served or gently spilled, your nervous system has pulled off this incredible feat with specific care. The brain can activate just a few motor units for delicate tasks like threading a needle, or recruit hundreds of them for more forceful actions like lifting a heavy suitcase. Your system is constantly adjusting based on the power you need, fine-tuning your movements through motor unit recruitment and rate coding. Fire more frequently, and you get stronger, smoother contractions, much like turning up the volume knob on a stereo for more intensity and output. Motion is not just about muscle contraction, it is about the grace of coordination and timing. This is where the cerebellum, the small but mighty structure at the back of your brain, enters the dance. It does not initiate movement, but it refines it by comparing your intended motion with actual feedback from your muscles and joints to make real-time corrections. Without it, your movements would be jerky and poorly timed. But the cerebellum ensures you do not overshoot when reaching for a falling pen, keeping you smooth and balanced. It even stores your motor learning, the quiet patterns that let you ride a bike or play an instrument without a single conscious thought. Deep in the brain, the basal ganglia are also hard at work, helping you start and stop actions with effortless ease. These interconnected nuclei filter out unhelpful or involuntary movements, and when they do not function properly, as in Parkinson's disease, one might experience tremors or rigidity. Even the simplest gesture involves many regions talking seamlessly, from the premotor cortex planning based on external cues to the supplementary motor area driving your internal decisions. The parietal lobe provides the spatial awareness to help you locate your limbs, as all these systems whisper to each other, milliseconds before emotion even begins. Imagine all of this happening while you dance or juggle, or climb a flight of stairs, for complex movements require intricate timing and feedback. Your nervous system does not just fire a command and hope for the best. It listens closely as your muscles move. Proprioceptors in your joints and tendons send continuous updates back to the brain, allowing for micro-adjustments mid-motion. Proprioception is that silent background awareness of where your body is, letting you close your eyes and still touch your nose without staring at your toes. In addition to this internal map, your system integrates information from your eyes and your skin, and even your inner ears to keep you balanced. The inner ear contains the vestibular system, filled with fluid and sensory hair cells that detect the orientation of your head. These signals help you track moving objects and orient yourself in space, though a spinning ride can leave you feeling wobbly and disconnected. Not all motor commands are conscious, for many are automatic, like the subtle adjusting of your posture or the simple act of blinking. These are handled by brainstem pathways and spinal reflexes that run in the background to keep you upright and breathing while you sleep. Eye movement is also deeply influenced by your emotions, as the limbic system connects to your motor centers. When you are nervous, your muscles might tighten, and when you are happy, you smile, for your brain weighs how you feel alongside the laws of physics. There is a delightful awkwardness when learning a new movement, like using chopsticks or practicing yoga for the first time. Your clunky movements are just your brain building new motor circuits, experimenting and adjusting like a play rehearsal. With repetition, the performance smooths out as control shifts from conscious centers to more automatic ones. Skilled dancers and athletes move fluidly because their neural pathways are deeply trained and working with practiced efficiency. Motor control is not perfect, as it remains vulnerable to fatigue and distraction and the passage of time. As we grow older, reaction times may slow and coordination might decline, requiring a bit more concentration for fine tasks. Yet, the nervous system remains remarkably adaptable, and with use and attention, it can stay functional and strong well into the later years of a long and beautiful life. Movement also brings a feedback loop of pleasure, as the brain often rewards activity with endorphins and dopamine, which are chemical signals associated with enjoyment and motivation, and even a soft sense of euphoria. This is why exercise and dancing and even stretching can feel so satisfying beyond just the physical benefits, for the nervous system does not just control motion, it celebrates it. Whether you are performing a pirouette or running for the bus, or simply reaching for your phone in the dark, your body is responding to a cascade of electrical commands and feedback signals and learned patterns. The muscles obey, and the joints flex, and the balance is adjusted, all in a quiet and lightning fast collaboration between brain and body. It is easy to overlook because it feels effortless, but inside that effortless moment is a masterclass in coordination. A whisper of intent becomes a wave of motion, where a thought becomes a step, or a gesture, or a graceful twirl. Whether it is elegant or goofy, it is still a marvel of motor magic powered by a nervous system that never stops moving. Your brain is not the same as it was yesterday, or last week, or even 5 minutes ago, and that is not a poetic exaggeration, but a reality of biology. With every experience, and every thought, and every attempt to remember where you left your keys, your brain is adjusting itself. It does not happen dramatically, like sprouting new lobes or rewriting entire regions, but it happens subtly and invisibly at the level of its connections. This ability to change is called neuroplasticity, and it is one of the most magical traits of the nervous system. Neuroplasticity simply means neural flexibility, and it refers to the capacity of the brain to rewire itself to form new connections and strengthen old ones, and sometimes prune away the ones that are no longer needed. It is not just a feature of the young or the injured, for it is happening all the time, even as you listen to this, and even as your brain quietly evaluates and adapts and optimizes its own inner circuitry. For a long time, scientists believed the brain was fixed after childhood, like a fully furnished house that only needed occasional dusting. But now we know that is not true, for the brain is more like a garden than a building, growing and trimming and reorganizing based on what you do and what you feel and what you need. Your brain is made up of billions of neurons, and each of these neurons can form thousands of synaptic connections with others, which are not etched in stone. They are maintained, or strengthened, or weakened, or eliminated depending on how often they are used. An idea often summarized by the phrase stating that neurons that fire together will also wire together. When two neurons are repeatedly active at the same time, such as one processing the sight of a cat and the other recognizing that it belongs to your neighbor, their connection strengthens over time. This makes the association faster and more reliable, until eventually you see the cat and instantly think of your neighbor, as your brain has used plasticity to form a shortcut. But it is not just about creating new connections, for neuroplasticity also involves synaptic pruning, which is the process of trimming away connections that are not used often. Think of it as the nervous system's way of tidying itself. For if a neural pathway does not spark joy or usefulness, the brain will quietly decommission it. This is not a loss, but an efficiency upgrade, as trimming the mental clutter makes room for more relevant and streamlined processing. This pruning is most active during childhood and adolescence, but it continues into adulthood in more subtle forms. If you stop speaking a second language, those language pathways may gradually weaken. And while the memory is not entirely gone, it has been tucked into the attic where the staircase might be a bit dusty. Learning something new, whether it is a skill or a habit or a piece of information, activates and strengthens specific circuits. Repetition is key here, for the more frequently you activate a pathway, the more the brain reinforces it. Practice matters because it is not just about getting better, but about laying down stronger tracks. Interestingly, neuroplasticity does not happen uniformly across the brain, as some regions are more flexible than others. The hippocampus plays a major role in forming new memories, and is one of the few areas where new neurons can actually be born throughout life. This process is called neurogenesis, and these newborn neurons can integrate into existing circuits and support learning, particularly in response to enriched environments and physical activity and novel experiences. Other regions like the primary visual cortex are most plastic early in life, but they are still capable of change if the right conditions are met. It turns out that novelty and attention and emotional significance can all boost plasticity, for the brain is more likely to rewire itself in response to things that are new and meaningful and challenging. Plasticity is not just about learning, for it is also a powerful tool for healing. When the brain is injured, such as after a stroke, neuroplasticity can help surrounding or even distant areas take over lost functions. This does not always result in a perfect recovery, but it is often enough to regain movement, or speech, or basic daily abilities. Therapies for stroke patients frequently focus on retraining the brain by encouraging it to forge new paths around damaged areas. There are also fascinating examples of sensory reorganization, where in people who are born blind, the brain regions that would normally process visual information often get recruited for other tasks like hearing or touch. The visual cortex does not just sit idle, but finds new ways to contribute, like helping interpret Braille through the fingertips, or enhancing auditory spatial awareness. The brain is less interested in rigid job descriptions and more interested in productivity. This ability to adapt is also the heart of habits, both good and bad, for when a behavior is repeated, the associated neural pathways become stronger and more efficient. Whether it is brushing your teeth or checking your phone or taking a walk after dinner, repetition builds automaticity. The brain does not ask whether a habit is helpful. It just follows the reinforcement, which is why breaking a habit requires more than just willpower. It means forming a new competing pathway and practicing it until it becomes stronger than the old one. Plasticity also plays a role in emotion and mental health, as chronic stress can reshape neural pathways in the amygdala and prefrontal cortex. Over time, this can make people more sensitive to stress and less able to regulate emotional responses. But the reverse is also true, for mindfulness and therapy and social connection can encourage the brain to form healthier patterns. Even talking about your thoughts or writing them down is a form of neural remodeling. Sleep is another powerful tool for plasticity, for during rest, and especially during REM sleep, the brain consolidates memories and strengthens new connections formed during the day. It is a little like saving your work before shutting down the computer. And without sleep, those new pathways are less likely to stick around. This is one reason why pulling an all-nighter might help you cram, but will not help you retain the material long term. Then there is the strange but compelling idea of phantom limbs, which is a dramatic example of plasticity in the sensory cortex. When someone loses a limb, the area of the brain that once processed sensations from that limb does not just go silent. Nearby regions begin to expand into that empty space, and some people can still feel sensations in a limb that is no longer there, even experiencing pain, because the brain has not yet updated its internal map. Over time, this can change, especially with the help of therapy or mirror training, providing a vivid demonstration of how flexible the brain can be even in the most unusual of circumstances. Technology is beginning to harness this plasticity as well, as brain-computer interfaces and neurofeedback and virtual reality rehabilitation are all designed to help people retrain or enhance their neural pathways. These tools do not work by brute force, but by gently nudging the brain to reconfigure itself and encouraging adaptability through feedback and repetition. Plasticity is not always glamorous, for it often means practicing things that feel awkward or frustrating, and it requires you to be patient with yourself when you are relearning or trying to overcome a deeply ingrained habit. But it is also a source of quiet hope, because no matter your age, your brain is never truly finished and remains a beautiful work in progress. It is a living and breathing and adaptable structure that listens to what you do and what you feel and what you pay attention to, changing its very nature in response. Right now, just by listening and thinking, you are strengthening certain connections and perhaps pruning others as your brain adjusts its internal landscape ever so slightly to make room for this information. Long after this moment has passed, those changes might linger, making it easier to recall a fact or understand a concept. or appreciate the sheer miracle of a brain that can learn how to learn. It is one of the most remarkable qualities of the nervous system that it can not only react and move and feel, but also reshape itself in response to the world quietly and patiently and relentlessly. This is a soft rewiring in the background of your everyday life, the gift of plasticity and the brain's quiet superpower. Memory is one of those magical abilities that we all rely on constantly, yet we rarely stop to question it until the moment it lets us down. You can recall a childhood jingle from 20 years ago with perfect clarity, yet somehow forget where you left your car keys just 5 minutes ago. This is not faulty wiring, but simply the way memory works, being beautifully complex and often mysterious, and sometimes hilariously selective. The nervous system does not store memories like files in a cabinet or data on a hard drive, but works through patterns of neural activity and strengthened connections and coordinated chemical changes. Memory lives in networks and not folders, always evolving, where some memories last seconds and others last a lifetime. Some arrive fully formed, while others hide until just the right smell of song brings them back in vivid and breathtaking detail. Broadly speaking, there are three main types of memory, which include sensory memory, and short-term memory, and long-term memory. Sensory memory is the briefest kind, holding on to raw input from your senses for just a few seconds, long enough for your brain to decide if it is worth paying attention to. You glance at a scene, or hear a passing sound, or feel a sudden brush of wind, and that moment lingers for a blink, before either fading or moving forward for processing. It is like the mental version of a loading screen, present for a moment and then gone. Short-term memory, sometimes called working memory, is where conscious thought happens, acting as the mental notepad that holds small amounts of information for a short time, usually from seconds to a minute. On average, most people can hold about 7 bits of information in their short-term memory, which is why phone numbers were originally designed with around that many digits. Working memory is flexible, for it is not just for storage, but for juggling ideas and solving problems and keeping track of what is happening in real time. It is the backstage assistant in the theater of the mind, quietly managing the props and cues that make coherent thought possible. Yet it is highly vulnerable to distraction, like when you walk into a room with a purpose, but forget it because you were distracted by a rogue sock on the floor. Then there is long-term memory, the vast archive of everything from your grandmother's birthday to the knowledge of how to ride a bike. Long-term memory is remarkably durable and includes facts and skills and events and emotional associations. Some of it is conscious and deliberate, known as explicit memory, while other parts are unconscious and automatic, like knowing how to tie your shoes or type on a keyboard without looking. These are implicit memories, and they often live deeper in the brain, formed through a process called consolidation. Turning a short-term memory into a long-term one is not instantaneous, for your brain needs time and often sleep to solidify those connections. This is why cramming for an exam might help you pass, but will not do much for remembering the material a month later. Sleep, and particularly deep and REM sleep, plays a huge role in moving memories into more permanent storage. Inside your brain, one of the key players in this process is the hippocampus, a seahorse-shaped structure in the medial temporal lobe. It does not actually store long-term memories, but acts as a processing hub that helps link together the sights and sounds and emotions and context of an experience so they can be reassembled later. Over time, the memory is distributed across various cortical areas depending on its content, with visual memories stored near the visual cortex and auditory elements near the auditory cortex. Interestingly, not all memories are treated equally. as emotionally charged events tend to be remembered more vividly. This is due in part to the amygdala, a region that processes emotions and communicates with the hippocampus to boost the significance of your experiences. If something scares you, or delights you, or makes you laugh until you snort, your brain adds a bit of extra glue to that memory to make it stick. Yet memory is not a perfect recording, but is reconstructive, meaning you are rebuilding it from pieces each time you recall it. This makes memories vulnerable to distortion, influenced by new information, or current emotions, or even the way someone else tells the story. Over time, your memories evolve, which can be charming or slightly inconvenient, depending on whether you are arguing about a board game from 5 years ago. One of the most curious things about memory is how selective it is, for your brain is constantly choosing what to store and what to discard, and it does not always prioritize what you would expect. You might forget what you had for lunch 2 days ago, but remember a random jingle from a cereal commercial you heard once as a kid. This is not a flaw, but a reflection of how the brain weighs relevance and repetition and emotional impact and context. Forgetting in many cases is not a bug, but a feature, as it helps clear out unneeded clutter to allow you to focus on new information and even protects you from being overwhelmed by emotional overload. The brain uses processes like synaptic weakening and interference, where new information overwrites older data to manage its memory load. It is not that the memory is gone forever, but it might just be harder to retrieve, especially if the retrieval cue is missing. Which brings us to the mystery of the keys. Or why do we so often forget where we put them? The answer is usually attention and not memory, because if you set your keys down while distracted, perhaps talking, or checking your phone, or thinking about something else, your brain does not tag the event as important. It gets filed under not worth remembering. And later when you try to retrieve the memory, there is nothing solid to grab onto. This is why making habits like always placing your keys in the same spot helps, for it offloads memory into routine. There are also practical techniques to boost your memory, and repetition is one of them. The more often you revisit a piece of information, the stronger the connections become, and spaced repetition is particularly effective for long-term retention. Chunking is another strategy where you group related bits of information into larger units, which is how you remember a phone number or break down a shopping list into categories like dairy and produce and snacks. Mnemonics and visualization and storytelling all work by making the information more memorable and engaging and emotionally resonant. Your brain loves patterns and images and narratives, and if you can turn a fact into a picture or a story, it is more likely to stick. AGA can affect memory, but it is not always a straightforward decline, as some types of memory, like general knowledge, can remain strong or even improve with age. Other types, like working memory, may slow down, but thanks to neuroplasticity, the brain retains its ability to form new memories and adapt, especially when it is stimulated by learning and social interaction and physical activity and sleep. Even in cases of memory loss, the brain is often more resilient than it seems. In conditions like Alzheimer's disease or other forms of dementia, memories may fade, but emotional memory, which is the feeling attached to an experience, often remains. A person might forget your name but still smile when they see you, because the emotional connection is still there, living in a deeper part of the brain. At its heart, memory is about meaning, for the brain remembers what matters. Whether it is the face of someone you love, or the smell of a childhood home, or the lyrics to that song you listened to on repeat during a particular summer, it holds on to the patterns that define who you are. It is a quiet archivist working behind the scenes to stitch together the story of your life and every moment you spend remembering. every chuckle at an old photo, and every name that dances just out of reach is a reminder of how dynamic and selective and deeply human memory really is. It is not just storage. It is the thread that connects you to yourself. Emotions are a bit like weather systems, being sometimes sunny and sometimes stormy, and occasionally foggy with a chance of snacks. They drift in and reshape your thoughts, coloring everything you perceive often without asking for permission. But while feelings can feel ephemeral or mysterious, their roots are deeply biological, orchestrated by your nervous system and shaped by evolution. At the center of this emotional orchestra is a collection of brain structures known as the limbic system. The term limbic comes from the Latin word for border, because this system sits like a ring around the brain stem, where ancient survival systems meet newer thinking regions. It includes several key players, such as the amygdala and the hippocampus and the hypothalamus and parts of the thalamus and cingulate cortex. Together, they form the core of your emotional processing network, where the amygdala acts as more than just a fear center, helping you detect threats and assess emotional significance. When something startles you, like a sudden noise or a shadow in the corner, the amygdala springs into action to prepare you for action. It is fast and efficient, though sometimes a little overzealous, which is why you might jump at a garden hose that vaguely resembles a snake. Meanwhile, the hippocampus is busy recording the context of where you were and what you were doing when an emotional event happened. It lays down the backdrop, allowing memories to be revisited later with vivid detail, which is why emotions are such powerful memory aids. The hypothalamus, sitting just below the thalamus, is a tiny but mighty structure that links the nervous system to the endocrine system. When activated by emotional stimuli, it sends signals to the pituitary gland to release hormones into the bloodstream. These hormones influence your body's responses, raising your heart rate and dilating your pupils and altering your digestion, all of which contribute to the physical feeling of emotion. This hormonal response is why emotions do not stay confined to the brain, for they ripple through the body to influence organs and muscles, and even your posture. Anxiety might tighten your stomach, while joy might give you a literal bounce in your step, and sadness can weigh down your shoulder. These are physiological realities shaped by nerves and hormones and feedback loops. The nervous system has two major branches involved in emotional regulation, which are the sympathetic and parasympathetic divisions of the autonomic nervous system. The sympathetic system prepares you for fight or flight, increasing your heart rate and redirecting blood to your muscles, while the parasympathetic system helps you rest and digest and return to baseline. Emotions often arise from the balance between these two forces, as fear typically ramps up sympathetic activity. You might feel a racing heart and shallow breathing and cold hands as your body prepares to either confront danger or escape it. Once the threat passes, the parasympathetic system works to calm things down, slowing your heart and relaxing your muscles to tell your body that you are okay now. But emotions are rarely that simple, for most feelings are blends, like fear mixed with excitement or sadness tinged with relief. Your brain does not just flip one switch, but activates multiple regions and compares past experiences while reading social cues. Sometimes it even consults your gut, quite literally, for the enteric nervous system resides in your gastrointestinal tract and communicates closely with your central nervous system. This is why anxiety can cause a stomach upset, and why you sometimes feel emotions in your belly before you fully understand them in your head. Chemicals also play a starring role in this drama, as neurotransmitters like dopamine and serotonin and norepinephrine and oxytocin modulate your emotional states in different ways. Dopamine is associated with reward and motivation, spiking when you achieve a goal, or eat something delicious, or receive a kind compliment. Serotonin influences your mood and sleep and appetite, and it is a major player in many medications used to treat the heavy clouds of depression. Norepinephrine, much like adrenaline, revs up your alertness and arousal, while oxytocin is often dubbed the love hormone because it strengthens social bonds and trust and attachment. It is released during hugs and eye contact, and those lovely moments when a dog looks at you like you are the center of the universe. These chemicals do not act in isolation, but interact in a constantly shifting neurochemical dance influenced by your genetics and environment and experience and behavior. Even something as simple as taking a walk in nature, or getting a good night's sleep, or hearing a favorite song can nudge your emotional chemistry in a different direction. Your brain is never emotionally neutral, for it is always balancing and recalibrating itself. Interestingly, the prefrontal cortex, which is the more recently evolved part of the brain responsible for reasoning and decision-making, plays a key role in regulating emotion. It evaluates the input from the limbic system and helps modulate responses, deciding if you should panic at a spider on the windowsill or calmly escort it outside. The prefrontal cortex weighs in and ideally keeps the amygdala from hijacking the entire operation. And in people with strong emotional regulation, this region tends to be especially active and well connected. Of course, emotion is not always about threat or reward, for it also plays a huge role in empathy, which is the ability to feel what others feel. Mirror neurons are specialized cells that fire both when you perform an action and when you observe someone else performing it. These neurons may help explain why we flinch when someone stubs their toe, or why a character's heartbreak in a film can leave us in tears. Social and cultural factors also shape how emotions are expressed and interpreted, for your brain comes with a universal emotional toolkit that is fine-tuned by upbringing and language and social norms. A smile means joy in most cultures, but the way we express grief, or anger, or embarrassment can vary widely. Even how we describe emotions can influence how we feel them. And giving a name to a complex feeling can sometimes shrink it down to a more manageable side. Emotions also serve a powerful evolutionary function, where fear helps us avoid danger, and anger protects our boundaries, and sadness signals a need for support. Joy reinforces beneficial behaviors, and even guilt, uncomfortable as it is, helps maintain social harmony by nudging us to reflect and repair our relationships. Emotions are not just noise, they are data, and the nervous system is the instrument that decodes and broadcasts them to the world. When things go awry, emotional regulation can become a challenge, where anxiety disorders and depression and mood swings can all reflect imbalances in the emotional network. This might be due to neurotransmitter dysfunction, or structural differences in brain regions, or traumatic experiences, or chronic stress. But because the nervous system is plastic and responsive, therapy and medication and mindfulness and social connection can often help rewire those circuits over time. Even the simple act of taking slow and deep breaths can calm the nervous system, as it activates the vagus nerve, which is a major component of the parasympathetic system. This tells the brain that we are safe and it is okay to relax, creating a feedback loop that reduces heart rate and softens tension and clears the emotional fog. Sometimes the most profound nervous system interventions are also the most gentle. What is most remarkable is how integrated all of this is. For emotions are not just brain states, but full body experiences shaped by history and chemistry and reflexes and memories and context. You do not just think emotions, you feel them in your skin and your chest and your breath and your gut. Whether it is the warm glow of affection, or the tight grip of fear, or the quiet ache of longing, every feeling is a symphony conducted by your nervous system. Sometimes it is loud and dramatic, while other times it is subtle and slow. And like any good symphony, it does not just affect the players, for it moves the audience, which in this case is you, in ways that can be profound and unpredictable and deeply human. The lights go out, and you crawl under the covers as your eyes close and the day slips away like a tide retreating from the shore. To the outside world, it may seem like nothing is happening, just a quiet and resting body. But inside your head, your brain is anything but idle. Sleep is not a passive shutdown, but one of the most active and mysterious states your nervous system enters. It is a nightly renovation, and a memory workshop, and an emotional recalibration, and occasionally a surreal theater of dreams. First, let us clear up a common misconception. For sleep is not a time when your brain turns off. Quite the opposite is true, as certain areas of the brain become even more active during parts of sleep than they are when you are awake. It is just that their priorities change, and while you snooze, your brain is sorting, and filing, and cleaning, and strengthening, all in the background like a housekeeping staff that only works after dark. Your sleep is divided into cycles, each lasting roughly 90 minutes and repeating throughout the night. These cycles are made up of several distinct stages categorized as non-REM and REM, which is short for rapid eye movement. Non-REM sleep comes in 3 stages, where the first stage is light and fleeting, acting as a transitional drift between wakefulness and slumber. In this phase, you might still hear the hum of the world around you, and a sudden noise or twitch might jolt you awake. This is the stage where hypnic jerks, those sudden full body spasms, often occur, acting like your nervous system doing a quick systems check before deeper rest. The second stage is deeper, where your heart rate slows, and your body temperature drops, and brain waves begin to shift into slower patterns. It is a place of true disconnection from the waking world, and while you are not yet in deep sleep, you are no longer easily disturbed. Your nervous system uses this time to settle into a low power state, lowering metabolic activity, and conserving energy, and preparing for what comes next. Then comes stage 3, which is deep sleep, also known as slow wave sleep. This is the most restorative phase, where brain waves become slow and high in amplitude, like rolling hills on a redoubt. Your muscles relax completely, and your body focuses on repair and recovery, releasing growth hormone to mend tissues and bolster immune functions. If someone tries to wake you during this phase, you will probably be groggy and disoriented, and possibly not very polite about it. But the real party starts during REM sleep, which is the phase most associated with dreaming. As your brain revs up, your eyes dart back and forth under your eyelids, and your breathing becomes irregular. Your brain waves start to resemble those of someone who's awake, yet your body remains largely paralyzed. This is a clever trick of the nervous system to keep you from acting out your dreams, as most skeletal muscles are temporarily turned off by inhibitory signals from the brain stem. It's a neurological lock to keep your sleep safe from your imagination, although dreams themselves remain something of a scientific puzzle. We know they occur most vividly during sleep, though fragments of dreams can appear in other stages too. Theories about why we dream range from emotional processing and memory consolidation to mental rehearsals, or even neural noise being interpreted into a narrative. Whatever the reason, your brain during REM is synthesizing images and emotions and memories into a kind of movie, often strange and sometimes meaningful, and occasionally starring people you haven't seen since 7th grade. But even beyond dreaming, sleep plays a vital role in memory and learning. Throughout the day, your brain gathers new information and stores it in a sort of mental inbox. During sleep, especially during deep non-REM and REM stages, the brain sorts through that inbox, deciding what to keep and what to discard, and where to file the important bits. This process is called memory consolidation, and it strengthens the neural pathways that support the things you have learned. It is one reason that getting enough sleep is so crucial after studying or learning a new skill, for even a quick nap can enhance performance on certain tasks. It is not just rest, it is rehearsal. While you snooze, the brain replays patterns of activity that occurred during the day, reinforcing connections and helping them stick. Sleep also has a remarkable effect on emotional regulation, as studies show that people who are sleep deprived tend to be more emotionally reactive and more irritable and less able to cope with stress. The amygdala, your brain's emotional alarm system, becomes more sensitive, while the prefrontal cortex, which normally keeps it in check, becomes sluggish. In other words, without sleep, your brain is like a toddler who missed their nap, being cranky and impulsive and a little dramatic. But with proper sleep, the brain seems to perform an emotional reset, helping you process the ups and downs of the day and smoothing out emotional rough edges. That weird dream about being late for an exam in a building made of cheese may not make sense, but it might still be doing something helpful behind the scenes. On a cellular level, sleep is also a time for cleaning house, as recent research has revealed that during sleep, the brain's lymphatic system becomes more active. This system helps clear out waste products that accumulate during wakefulness, including excess proteins linked to neurological diseases like Alzheimer's. Think of it as a nightly rinse cycle for your brain, subtle and essential, and only possible when you are not using it to do more active tasks. Importantly, neurons never truly stop working, even during the deepest sleep. Their patterns shift and their priorities change, but they remain active, keeping your heart beating and lungs expanding and internal environment stable. The autonomic nervous system continues its background magic, regulating temperature and digestion and hormone release and 1,000 other tasks that do not punch out just because you have gone to bed. Even in dreams, neurons are firing across sensory areas, and motor planning zones, and emotional centers. The brain does not just store old memories, it recombines them, and plays with them, and sometimes creates new associations. This flexibility may be part of what makes humans so creative, for sleep might not just help us remember what happened, it may help us imagine what could be. Despite its importance, sleep is still a bit of a biological mystery. We know what happens during different stages, and we can track its benefits, but the full reason why sleep is so essential is still being uncovered. Dolphins sleep with half their brain at a time, and birds can sleep mid-flight, and even fruit flies show sleep-like behavior. It is clear that whatever sleep is doing, it is worth the risk of lying motionless for hours in a world full of predators. In humans, the effects of sleep deprivation are quick and profound. For after just one sleepless night, attention and coordination and memory begin to falter. Prolonged sleep loss affects metabolism and immune function and mood and even gene expression. It is not just about feeling tired, for sleep is woven into every aspect of health and cognitive function. That is why the sleepy brain is not a lazy brain, but a busy and purposeful and hard-working organ that just happens to do its best maintenance work while you are out cold. It repairs and sorts and cleans and creates, all while you dream of penguins or parallel universes, or accidentally showing up to work in your pajamas. So the next time you lie down, think of it not as checking out, but as checking into a quiet and restorative neural retreat. Your nervous system knows what to do, and all you have to do is drift. You do not think about making your heart beat, and you do not consciously tell your stomach to start digesting lunch, or remind your lungs to breathe in before you yawn. These things just happen, running smoothly in the background like an invisible operating system, managing the most essential parts of your existence without ever demanding your attention. That system is called the autonomic nervous system, and it is one of the quietest but most powerful supervisors in your body. The word autonomic comes from autonomous, which means self-governing, and that is exactly what this system does. It takes care of all the vital functions that do not require your conscious input, such as your heartbeat, and blood pressure, and breathing rate, and digestion, and pupil dilation and body temperature. Even how much you sweat is modulated by this built-in life support system. It is not glamorous, but it is incredibly efficient, a tireless background orchestra tuning and adjusting every second of the day. The autonomic nervous system has two major branches, which are the sympathetic and the parasympathetic. These two systems are often described as working in opposition, but they are really more like dance partners, each taking the lead at different times depending on what life throws at you. Let us meet the more dramatic of the two first, the sympathetic nervous system, which is your fight or flight mode. This is the inner alarm system that gets triggered when something startling or stressful occurs. When your brain perceives a threat, whether it is a snake in the grass or an unread email with the subject line urgent, the sympathetic system springs into action. In response, it kicks off a rapid series of physiological changes, where your heart rate speeds up to pump more oxygenated blood to your muscles. Your pupils dilate to let in more light and improve vision, and airways open up to help you breathe more deeply. The digestive system hits the brakes, because who needs to digest a sandwich when there might be a tiger nearby? Blood is rerouted away from the stomach and toward the limbs, readying you to run or react. All of this happens within the briefest of moments, and you do not even have to lift a single finger. That sudden rush of adrenaline is thanks to your sympathetic nervous system, working in a secret harmony with the endocrine system. It sends quiet signals to the adrenal glands, which are perched just above your kidneys like small and faithful guardians. They release hormones such as adrenaline and norepinephrine into your blood, turbocharging your response to the world around you. Of course, most of us are no longer dealing with tigers in the grass, but modern life still gives the sympathetic system many excuses to speak. Public speaking, or deadlines, or unexpected phone calls, or loud noises, or even an awkward pause in a conversation can trigger it. Your body does not always know the difference between a threat to your life and a moment of mild embarrassment. If a moment feels urgent, the response is exactly the same. That is where the parasympathetic nervous system arrives, like a gentle friend after a long day. This is your rest and digest mode, the calming counterpart to the high alert enthusiasm of the sympathetic system. But its sacred job is to bring everything back to the baseline. After the storm has finally passed, it slows your heart rate and promotes your digestion and constricts your pupils back to their normal size and encourages deep relaxation and repair. This system is largely responsible for helping your body perform its quiet maintenance. It helps produce your saliva and stimulate your intestinal activity and manage the slow and steady business of keeping you alive when nothing dramatic is happening. It also supports your immune function and sexual arousal and the conservation of your precious energy. In short, it is the built-in spa day of your nervous system. One of the key pathways here is the vagus nerve, a long and meandering nerve that extends from your brainstem down through your chest and deep into your abdomen. It is involved in regulating your heart rate and digestion and even your vocal cord function. It plays a role in inflammation and immune signaling, and stimulating it through slow breathing, or humming, or singing, or cold exposure can reduce your stress and improve your well-being. The balance between these two systems is known as your autonomic tone. Ideally, your body shifts smoothly between them as it is needed. If you are in danger, the sympathetic system takes the lead. But once you are safe, the parasympathetic system brings you back to a state of absolute calm. Yet, modern stresses can sometimes cause the sympathetic system to stay active for much longer than it should. This leads to chronic tension and elevated blood pressure and a deep fatigue. Fortunately, your nervous system is highly responsive to the cues from your environment and your own behavior. Deep breathing sends signals to the brain that you are safe, which slows the heart rate and activates the parasympathetic response. Meditation and stretching, and nature walks, and even laughing can tip the balance toward deep relaxation. Interestingly, some of your organs are controlled by both systems in a kind of push and pull relationship. The heart, for example, speeds up under sympathetic influence and slows down under parasympathetic control. The digestive system, on the other hand, is inhibited by the sympathetic system and stimulated by the parasympathetic system. It is like having two managers with very different priorities, one focused on emergency preparedness and the other on daily operations. Not every organ is under such dual control, for your sweat glands are primarily managed by the sympathetic system. That is why anxiety often leads to clammy palms or a suspiciously damp shirt at the worst possible moment. It is not your fault, for it is only biology trying its best to keep you cool under the pressure. The autonomic nervous system also plays a crucial role while you are sleeping. As you begin to drift off, your parasympathetic activity increases, helping your body to wind down. Your heart rate slows, and your blood pressure drops, and your digestion resumes its unhurried and peaceful rhythm. If something wakes you suddenly, perhaps a noise, or a bad dream, or a mystery bump in the night, the sympathetic system can kick in almost instantly. It brings you to full alertness before you are even fully aware of what is happening. Another fascinating feature of this system is its involvement in your emotional responses. Think about blushing, or a flushed face during anger, or a lump in your throat when you are sad, or the butterflies in your stomach before a big moment. These are the visceral expressions of your emotional states, routed through these autonomic pathways. Your nervous system does not just manage your body, it expresses your inner world through it. Disorders of the autonomic nervous system are rare, but they can have wide-ranging effects. Conditions such as dysautonomia, or orthostatic hypertension, or vasovagal syncope involve disruptions in this regulation. These can cause symptoms like dizziness, or fainting, or abnormal heart rates, and difficulties with temperature control or digestion. Because this system touches so many parts of your body, even minor dysfunctions can be disruptive. Yet, most of the time, this system functions quietly and flawlessly, keeping you balanced between action and rest, and danger and safety, and tension and release. It is the part of the nervous system that never takes a bow or demands applause, but it still deserves a standing ovation. So, the next time you find your heart racing, or your breath quickening, or your shoulders relaxing after a deep exhale, remember your autonomic nervous system is hard at work. It is the silent supervisor, always listening and always adjusting, and keeping you just the right amount of ready. Not too tense, and not too loose, just enough to keep you alive and responsive. Whether you are running from imaginary tigers, or enjoying a very real nap, you are being cared for. If the neurons are the electrical wires of the body, then myelin is the insulation that keeps the current running cleanly and quickly. It is not flashy, but it is absolutely essential. Without myelin, your thoughts would move like molasses, and your reflexes would crawl, and simple movements would become frustrating puzzles of delay. Myelin is the unsung hero of the nervous system, a fatty and whitish substance that wraps around certain nerve fibers like a cozy and high-performance blanket. It ensures that your messages travel with speed and precision. Let us back up for a moment. For every time you move a finger or blink an eye, or even ponder a daydream, electrical impulses race through your neurons. These impulses are called action potentials, and they travel along those long projections known as axons. For some neurons, those axons can stretch surprisingly far, several feet in fact, especially in the motor neurons that run from the spinal cord down to the toes. Now, imagine trying to send a signal down that kind of length with no insulation at all. The message would lose its energy and slow down, and possibly leak into the surrounding environment. That is where myelin steps in, acting like the rubber coating on electrical cables. In the central nervous system, which is your brain and spinal cord, myelin is produced by specialized cells called oligodendrocytes. Each of these cells can extend its processes to multiple axons, wrapping segments of each in layers of myelin. In the peripheral nervous system, which includes all the nerves outside the brain and spinal cord, a different type of cell takes over, known as the Schwann cell. These cells wrap around axons like cinnamon rolls, forming a thick and protective sheath. Myelin is not applied as a continuous tube, but it wraps axons in segments, leaving tiny gaps between the insulated parts. These gaps are called the nodes of Ranvier, and they are not design flaws, but brilliant features. When an electrical impulse reaches one of these nodes, it briefly depolarizes the membrane, and then jumps to the next node. This leapfrogging process, called saltatory conduction, allows the signal to travel much faster than it would if it had to move steadily down the entire axon. It is a bit like skipping every other step on a staircase instead of taking each one, which is much faster and still just as reliable. Thanks to myelin, some nerve impulses can travel at speeds of over 100 meters per second. That is fast enough for you to yank your hand back from something hot before you even register the pain, or to catch a falling object without consciously thinking about it. It is not just speed for the sake of speed, for it is about survival and safety and smooth coordination. And here is something fascinating. Not all axons are myelinated. Neurons that need to carry fast and sharp or long-distance signals usually get the VIP treatment with myelin sheets. These include your motor neurons and the sensory neurons involved in touch and proprioception, and many of the neurons found within your reflex arcs. But other neurons, particularly those involved in slower or more diffuse signaling, remain unmyelinated or only lightly coated. Pain signals, for example, often travel along thinner and unmyelinated fibers, which is why the burning ache of an injury may arrive moments after the initial sharp jab. The nervous system knows how to prioritize its traffic, and myelin is not fully formed at birth. In fact, much of the process of myelination happens after birth and continues well into your young adulthood. This slow and staggered development is why babies do not pop out during algebra or acrobatics, as the nervous system needs time to wire itself efficiently. You can see this progression in action as babies learn to crawl and walk and talk, and eventually master things like shoelaces and sarcasm. Myelin is what turns those early wobbles into smooth and controlled movement and refined cognitive skill. But like all biological systems, myelin can be vulnerable. And one condition that brings this into sharp focus is multiple sclerosis. This is a chronic illness in which the immune system mistakenly attacks the myelin in the central nervous system. When the myelin sheath is damaged, the electrical signals along the axon become slowed or disrupted, like a frayed wire that can no longer carry current properly. This can lead to a wide range of symptoms depending on which areas are affected, and in this condition, the symptoms vary from person to person. Some may experience muscle weakness or coordination problems, while others might notice blurred vision and fatigue and numbness or cognitive changes. These symptoms can come and go and flare up unexpectedly or gradually worsen, reminding us just how vital and fragile myelin really is. When myelin is damaged, the body attempts to repair it, as oligodendrocytes can sometimes regenerate lost myelin, especially in the early stages of the disease. But over time, if the damage is repeated or widespread, the axons themselves can become injured, leading to more permanent neurological deficits. Research is ongoing into how to protect and regenerate or replace myelin, an area full of both challenges and hope. Beyond multiple sclerosis, other conditions can also affect myelin, such as genetic disorders like leukodystrophies that disrupt the formation of myelin in children. Certain toxins and vitamin deficiencies and infections can also damage myelin or interfere with its maintenance. Even prolonged stress or lack of sleep may influence how effectively the brain maintains its myelin, though this area is still being explored. Yet, despite these vulnerabilities, myelin is an incredibly durable structure, and in most people, it lasts a lifetime. It faithfully wraps and maintains nerve fibers across billions of signals a day, rebuilt and maintained by glial cells that monitor and support the health of the nervous system. They're like quiet custodians, keeping things in top shape while the neurons do their thinking, and moving, and sensing. Interestingly, learning a new skill can also influence your myelin production, as studies show that when people engage in sustained mental effort, their brains may respond by increasing myelination in relevant areas. This suggests that myelin is not just about insulation, but also about optimization, as the nervous system is always trying to find the most efficient way to do things. Even in adulthood, myelin can continue to adapt to new experiences, which is a quiet testament to the plasticity of your nervous system. It adjusts and repairs and strengthens and occasionally falters, but it never stops working to keep your thoughts running smoothly. So whether you are leaping out of the way of a rogue frisbee, or solving a puzzle, or simply blinking in surprise, remember that each of those actions depended on the speed and fidelity of neural communication. None of that would be possible without myelin, the silky and spiraled wrapping that turns a flicker of neural intention into action at the speed of thought. It is not the star of the show, but without it, the whole production would grind to a halt, one sluggish signal at a time. Neurons tend to steal the spotlight, for they fire the action potentials, and carry your thoughts, and move your muscles, and relay your feelings. They are the ones with all the flashing lights in the brain diagrams, and the ones everyone points to when talking about intelligence and emotion and memory. But behind those high-performing showboats is a vast and loyal support crew, the glial cells quietly holding everything together. While they do not conduct electricity like neurons, without them your brain would be about as useful as a theater without a backstage. The name glia comes from the Greek word for glue, which gives a rather humble impression, as though they are just there to keep things stuck in place. But that is like saying a city sanitation department just takes out the trash, when in reality glial cells do everything from regulating blood flow to delivering nutrients. They repair injury and prune synapses, and even influence how neurons communicate, acting as the architects and janitors and nurses and electricians of the nervous system. They outnumber neurons by a significant margin, beginning with the astrocytes, named for their star-shaped appearance under the microscope. These cells are the multitaskers of the brain, maintaining the chemical balance around neurons and mopping up excess neurotransmitters. They regulate ions and help guide developing neurons during early brain growth, acting like a colleague who restocks the coffee and fixes the thermostat. Astrocytes also form part of the blood-brain barrier, a semi-permeable shield that controls what substances in the blood are allowed into the delicate environment of the brain. This is a vital job, for the brain needs a constant supply of oxygen and glucose, but it also needs protection from toxins and pathogens and certain chemicals. Astrocytes help regulate what gets in, keeping the peace at the border, and when injury strikes, they leap into action. They swell and change shape to form a kind of scar tissue around the damaged area, which can be both helpful and problematic. It seals off the danger zone, and though it sometimes interferes with regrowth, they are doing their best under pressure to keep the rest of the brain running smoothly. Then there are the microglia, the brain's own personal immune force, which are the smallest of the glial cells but pack a punch, constantly patrolling the nervous system. They look for signs of trouble, like dead cells, or foreign invaders, or proteins that do not belong. When they find something suspicious, they respond swiftly, engulfing and digesting the threat in a process called phagocytosis. It is not glamorous, but it is absolutely critical for your health. Microglia also help during development by trimming synapses, for when the brain is forming, it tends to create far more connections than it actually needs. These cells act like sculptors, carving away the extra connections to refine and streamline the network, a process that continues into adolescence and plays a key role in shaping how your brain functions. Interestingly, researchers have discovered that microglia are sensitive not only to injury and infection, but also to stress and sleep deprivation and chronic inflammation. When overstimulated, they can become overzealous, contributing to conditions like neurodegenerative disease or chronic pain. Like many things in biology, balance is everything, and even the immune cells of the brain need to know when to act and when to stand down. Next on the roster are the oligodendrocytes, which are arguably the most fashion-forward of the glial world, given their talent for wrapping axons in myelin. Each oligodendrocyte can extend multiple arms to different neurons, sheathing segments of axons in thick and fatty insulation. This insulation speeds up the transmission of electrical signals like fiber optic cables laid across a city, ensuring that messages arrive quickly and clearly. The importance of myelin is hard to overstate, for without it, thoughts would crawl, and reflexes would falter, and coordinated movement would be an exhausting mess. Oligodendrocytes do not just install this insulation. They maintain it by checking for damage and making repairs as needed. In the peripheral nervous system, this role is played by Schwann cells, which operate much the same way but with a more one-to-one relationship. Each Schwann cell wraps around a single segment of a single axon, and they also assist in regeneration. If a nerve is damaged outside the brain and spinal cord, Schwann cells can help guide the regrowth process, which is part of why peripheral nerves can sometimes recover while central nervous system damage is often more permanent. But glial support does not stop there, for there are also ependymal cells which line the ventricles of the brain and help produce cerebrospinal fluid. This clear liquid cushions the brain and removes waste and keeps things chemically balanced, acting like the brain's private spa. All of these glial cells work together in intricate harmony, for while neurons may get the headlines, they rely entirely on this support. Neurons are needy, requiring constant nourishment and protection from chemical imbalances and stable temperature and timely cleanups of their waste. In recent years, our view of glial cells has shifted dramatically, for they are no longer seen as just support staff but as active participants in neural function. Astrocytes, for example, are now known to influence synaptic transmission by releasing their own signaling molecules, sometimes referred to as gliotransmitters. Glia also seem to play a role in learning and memory, suggesting that the interaction between neurons and astrocytes affects how long-term memories are stored and recalled. It is a partnership and not a solo act, for even in mental health, glial cells are gaining attention. Depression and anxiety and schizophrenia and neurodegenerative diseases have all been linked in some way to glial function, whether it is inflammation from overactive microglia or disrupted communication from damaged oligodendrocytes. The quiet work of glia can have profound effects. There is also something poetically reassuring about glia, for they do not demand the spotlight or fire action potentials, but they are absolutely essential. They show up day after day, regulating and supporting, and cleaning up, reminding us that the most important jobs are not always the loudest. Behind every action, and every thought, and every flicker of consciousness, there is a quiet workforce making sure the system runs. You might not hear them, but without them, you would not hear anything at all. The nervous system is a marvel of design, a delicate and intricate web of circuits and signals that manages everything from muscle twitches to symphonies of thought. Most of the time it hums along beautifully, like a well-tuned orchestra playing the symphony of life without missing a beat. But sometimes things do not go quite as planned, for the nervous system is vulnerable to disruptions that can come in many forms. These can be tiny chemical imbalances or larger structural injuries, resulting in conditions we call neurological disorders. Before we dive in, it is worth noting that this is not a tale of doom and gloom, for medicine and the human spirit continue to shine here. Advances in understanding and treatment have brought enormous progress every day, and in many cases, people adapt and live meaningful and rich lives. Let us begin with Parkinson's disease, a progressive disorder that primarily affects movement. It is caused by the gradual loss of dopamine-producing neurons in a part of the brain called the substantia nigra. Dopamine is crucial for smooth and coordinated muscle activity, and without enough of it, the motor circuits start to falter. The common symptoms include tremors starting in the hands, and stiffness, and slow movement, and balance difficulties. Simple tasks like buttoning a shirt can take more effort, and it can also affect mood, and sleep, and digestion, and even smell. While there is currently no cure, treatments like levodopa can temporarily restore dopamine levels, giving the brain back its missing chemical messenger. In some cases, deep brain stimulation acts as a kind of pacemaker for the brain to reduce tremors and improve control. Then there is epilepsy, a condition marked by recurrent and unprovoked seizures. A seizure is like a sudden electrical storm in the brain, where a group of neurons fires in a highly synchronized and abnormal way. This can lead to temporary changes in awareness or movement or sensation, and the experience varies widely depending on where the storm is located. Some people may experience a brief lapse in consciousness, while others might have involuntary movements or sensory changes. It is a common condition that affects people of all ages, and most can manage it effectively with medications that help stabilize the electrical activity of the brain. A seizure is a sudden surge of electrical activity in the brain, like a thunderstorm in the neural sky. These surges can affect movement and awareness and sensation, or even emotion, depending on where in the brain they occur. Some seizures are dramatic, with shaking limbs and loss of consciousness, while others are far more subtle. It might be a brief pause in conversation, or a staring spell, or a sudden sense of déjà vu, lasting a few seconds or several minutes. For people with epilepsy, The unpredictability of seizures can be one of the most challenging aspects. Causes may include genetic factors and head injury and infections and stroke or developmental abnormalities, though sometimes the exact cause is not known. The good news is that it is often treatable, with medications controlling seizures for the majority of people. For those who do not respond to medication, there are surgical options and dietary therapies and neurostimulators that can help. Epilepsy does not define a person, for it is a condition and not an identity. With the right support, many people live full and independent lives. As awareness helps reduce stigma and build accommodating communities, let us look at stroke, one of the most common and sudden neurological events. A stroke happens when blood flow to part of the brain is interrupted, either by blockage or by bleeding from a ruptured vessel. Since the brain relies on a constant supply of oxygen and nutrients, even a short disruption can cause cells to suffer or die. The effects depend on where the stroke occurs, impacting speech and language on the left side, or spatial awareness on the right. Some people have weakness or paralysis on one side of the body, or changes in vision, or difficulties with balance and coordination. In some cases, a stroke can also affect personality or cognitive function. Time is critical, and the faster a person gets treatment, the better the chances of minimizing damage. There is a helpful guide to remember, involving face drooping, and arm weakness, and speech difficulty, as a sign that it is time to call for help. Quick recognition can save lives and reduce disability. Recovery from stroke varies, but the brain is remarkably adaptable through neuroplasticity. Through this process, other parts of the brain can take over lost functions. Rehabilitation is a team effort involving therapists and caregivers, where progress happens in big leaps or tiny and meaningful gains. Other conditions also deserve mention, such as multiple sclerosis, where the immune system attacks the myelin sheath. Alzheimer's disease is a degenerative condition that gradually erodes memory and thinking skills. Amyotrophic lateral sclerosis, or ALS, affects motor neurons and leads to progressive muscle weakness. These conditions, though each very different, highlight how diverse and complex the nervous system can be. But in every case, there is a growing body of research and compassion and support. Scientists are exploring new treatments using gene editing and stem cells and targeted immunotherapies. Devices and apps are helping with daily tasks and communication and tracking symptoms. Support groups and communities are making it easier to share experiences and resources and encouragement. There is a deeper kind of hope that comes from resilience. As people become experts in adaptation, they learn to listen to their bodies and adjust routines and ask for help when needed. They build new pathways as their brains find alternate ways to communicate and move and remember. The nervous system is a living network of connection, not only within the body, but between people. Even when the system breaks, there is beauty in how it tries to heal and rewire and find workarounds. We see the dignity of persistence and the quiet strength it takes to live with uncertainty. While neurological disorders can be serious, they are a testament to how astonishing the nervous system truly is. It is not because it is perfect, but because of how much it can endure and how much it can adapt. There is always more to learn, and more hope to be found, and more stories of courage and creativity. The nervous system has always been quietly extraordinary, managing everything from your morning stretch to your deepest thoughts. But imagine if this system could one day be upgraded through real advances that restore and enhance and extend our abilities. We live in an age where science taps into the brain's electrical language with results that are nothing short of astonishing. Brain-computer interfaces, or BCIs, allow direct communication between the brain and an external device through thought alone. There is no keyboard, and no mouse, and no voice commands, just the silent flow of your intent. These systems detect patterns of electrical activity and translate them into digital signals to control a robotic arm, or a cursor, or even a drone. People have literally flown drones with their minds, and BCIs offer promise for those with paralysis or locked-in syndrome. Individuals have used implanted electrodes to type messages, or control wheelchairs, or grasp objects with robotic limbs. The systems are not perfect yet, for they require training and advanced hardware. But progress has been faster than expected. One reason this works is that the brain continues to issue motor commands, even when disconnected from the body. Someone who has lost the ability to move their hand can still think about moving it, and the motor cortex still lights up. BCs tap into those signals and redirect them elsewhere, like rerouting traffic when a bridge is out. The brain says move, and the system finds another way to make it so. Researchers are also exploring the reverse, feeding information back into the brain through sensory prosthetics. Artificial retinas and cochlear implants already do this, capturing data and converting it into electrical signals for the brain to interpret. The results vary, but many people with cochlear implants are able to hear well enough to understand speech and music and environmental sounds. This progress is a true marvel of neuroengineering, unfolding in the quiet visual realm, where efforts are now underway to develop retinal implants and even direct stimulation of the visual cortex to restore the precious gift of sight. It is early days in this journey, but the idea of restoring vision, even if only partially, to those who are blind, is no longer just a distant dream. Some researchers are even asking if we can restore basic vision. Then could we eventually create entirely new kinds of perception, such as infrared sight or ultraviolet awareness, or even sensory input from remote and distant environments? It seems the nervous system may not be limited to its factory settings forever. As we learn to expand the horizons of what it means to truly see, another groundbreaking area is neuroprosthetics, where artificial limbs and devices interface with the nervous system to restore movement and sensation. These are not just robotic limbs controlled by external buttons or switches, but advanced versions that connect to nerves or muscles directly, allowing users to move them using natural signals, and in some cases, to even feel the softness of touch or the weight of pressure. This feedback loop of movement and sensation is key, making a prosthetic feel like a part of the body rather than just a tool. As new devices transmit sensory information back into the peripheral nerves, they gently trick the brain into believing the sensation is coming from a real hand or foot. And while it is not quite indistinguishable from the original, it is close enough to change lives forever. In clinical neuroscience, there is a growing interest in using electrical stimulation to treat conditions like Parkinson's disease and depression and epilepsy. Deep brain stimulation involves electrodes implanted into specific brain regions, helping thousands of people with Parkinson's to reduce tremors and improve their mobility. This technique delivers targeted pulses of electricity to regulate abnormal neural activity, much like tuning a radio to a clearer and more beautiful signal. More recently, researchers have been experimenting with non-invasive brain stimulation techniques, such as transcranial magnetic stimulation and transcranial direct current stimulation. These approaches use magnets, or small electrical currents on the scalp, to modulate brain activity, showing promise in treating depression and anxiety, and even boosting cognitive performance in some cases, though the effects can vary and are still being carefully studied in the quiet of the lab. Meanwhile, neurogenetics and stem cell therapy are opening doors that seemed sealed shut just a decade ago. As we begin to understand the genetic basis of certain neurological conditions, scientists are exploring gene therapies that can fix faulty instructions at the very source, while stem cells are being studied for their potential to replace damaged neurons, or regenerate spinal cord tissue, or protect against the slow fade of neurodegeneration. There is even research into synthetic synapses, which are lab-made connections that mimic the properties of real ones. And these could one day be used to repair or enhance neural circuits, or even to create hybrid brain-machine systems. It is still very theoretical, but it raises interesting questions about where biology ends and technology begins, as we see more integration of neuroscience with artificial intelligence on the horizon. Artificial intelligence can help decode the complex activity of your brain and recognize patterns, and even adapt to the neural signals of a user in real time. This could make brain-computer interfaces faster and more intuitive and more useful for every task of your daily life. Think of a system that learns your mental rhythms and adjusts its behavior to suit your intent, like having a highly empathetic co-pilot in your own mind. Of course, all of this innovation comes with important ethical considerations, such as how much control we should have over brain activity. We must ask what privacy looks like when thoughts can be decoded by machines, and how we make these technologies safe and accessible and respectful of individual autonomy. These are questions scientists and ethicists and society at large are beginning to wrestle with, not because we are already living in a world of mind-reading helmets, but because we are getting closer than most people realize. It is worth noting that not all future breakthroughs have to be high-tech, for some of the most powerful interventions may continue to be low-tech. High-impact practices like mindfulness and sleep hygiene and exercise and connection with others all promote neuroplasticity and support your mental health. The future of the nervous system is not just about replacing what is lost, but also about nourishing what is already there. Even with all the gadgets and implants and interfaces on the horizon, one truth remains beautifully unchanged. The human brain is already an incredible system, for it grows and adapts and learns and dreams and loves all through soft tissue and electrical whispers. The technologies we develop will likely never replicate its full complexity, but they might help us heal it, or support it, or communicate with it in ways we could not before. Imagine a future where a person with paralysis can type just by thinking, and where a person who is blind can navigate a room through a synthetic visual signal. Imagine a world where depression is treated not just with medication, but with personalized neural feedback, and where aging brains are gently supported to retain memory and clarity longer. That future is not light years away, for in many labs and clinics, it is already being built. So while the nervous system may be quiet, its future is anything but, humming with the promise of healing, and of enhancement, and of new ways to connect, whether through biology or technology, or some elegant fusion of the two. We are just beginning to understand how to support this extraordinary network. One day, a thought alone might be all it takes to shape the world around us. As we come to the end of our quiet journey through the nervous system, take a moment to sit with the wonder of it all. Within you is a vast pulsing network, a symphony of cells and signals, and silent messages working tirelessly to carry your thoughts and shape your feelings and move your body through the world. It does this without asking for praise or applause, and without needing your conscious attention. The nervous system is the most devoted communicator of your body, being soft-spoken and incredibly precise and always on call. From the spark of a single neuron to the vast loops of emotion and memory and sensation and sleep, every part of you is connected by this gentle electrical whisper. It holds your stories and your dreams and your reflexes, and your quiet moments of awe. It carries you through joy, and through grief, and through the ordinary rhythm of daily life. Somehow it still finds time to let you laugh at a bad pun, or jump at a surprise sneeze, or remember the smell of the kitchen of your grandmother. All of this, every blink and breath, and bittersweet memory, is made possible by your nervous system quietly humming along in the background. So, as you settle in for sleep, give a little gratitude to your inner circuitry. It has worked hard today, and tonight it will keep watch while you rest, replaying your memories, and cleaning house, and restoring balance, and preparing you for whatever tomorrow brings. If you enjoyed this gentle exploration of the quiet magic of the brain, I would be ever so grateful if you left a like or subscribed to the Sleepy Club. It helps more curious minds find their way here. And before you drift off, I would love to know where in the world you are listening from tonight, and what time it is where you are right now. Sleep well, and may your neurons fire softly until morning. Good night.